you, Fabian. So yeah, it's good to be here. A bit nerve-wracking also, but good nonetheless. So yeah, I've just recently completed a 4-year NGD with ROLI, which is like a PhD, but you work for a company at the same time. So it's like 3/4 company work and 25% doing like academic publications. And the idea is that you do some research inside the company and get some novel IP for them and novel research ideas at the same time as getting academic publications. So you get the best of both worlds. My research was looking at visualizing musical timbre in real time, so like using musical timbre features to drive generative visualization algorithms. And as part of that, like to facilitate that research, I developed this real-time feature extraction tool using JUCE. And today I'm going to talk about developing that tool. It's not a talk about why the tool is good. It's not very good. It's about developing the tool and the process I went through while developing it. So, yeah, let's move on. So I will first give a brief overview of feature extraction. Can I get a show of hands who is familiar with feature extraction, audio feature extraction? Cool, so it'll be a brief overview. After that I'll give an overview of the tool I made, the features it has, the functionality it has, and the motivations behind its development. And then I'll go into detail about some issues I faced during the development process and the solutions, the way that I approached those issues. And finally, I'll use that to lead into a wider discussion on the differences in coding practices between academia and industry. So I was kind of sitting in the middle of both during this research project, and I got some insight in that. So feature extraction, as most of you know, is the task of analyzing an audio signal to extract numerical descriptors about the audio. There are a lot of different features to think about. This paper by Peters et al. Is a good starting point if you want to learn more. But yeah, there are a lot to think about, and they can describe multiple different aspects about the audio, like how the amplitude varies over time or how the frequency varies over time. The tool that I developed deals mainly with spectral and harmonic features, so that's how the overall spectral envelope varies over time and how the harmonic peaks and the peaks in that spectral envelope vary over time. So they're the two types of features that I focused on, and the process of extracting those kinds of features often involves getting an STFT, which is when you cut the audio signal into very, very small windows and overlap them, and then for each window you apply an FFT and get the frequency response, the frequency envelope, and then you get the features of the spectrum for each window, and they give you sort of like keyframes in an animation, so you can see how those features vary over time, and you can map them to a visualization algorithm, for example. So yeah, the tool that I developed was designed for minimal setup and like ease of use, and so that you could use it in multiple different contexts. And it runs fairly nicely, but there's still a lot to improve and a lot of features I could add and ways that I could iterate on it. And as I mentioned before, I'm not here to advertise it. I just want to talk about the process of developing it. So to that end, I want to point out that there are other better tools available for this. libextract is a good one. It has like wrappers for Max MSP and PD. And there's also, I want to point out, Sound Analyzer by Adam Stark, which the reason I'm pointing this one out is it's very, very similar to mine. So it has direct access to OSC features, and I believe he developed it with the same use case in mind, so that like live audio-visual performances. Again, his feature set is much more extensive than mine, so maybe use that one. So also he developed it as a plugin. So mine is standalone, his is a plugin, so you use his in a DAW, so you get access to the DAW's multi-track capabilities and pre-processing capabilities, which is quite nice. So yeah, there's a lot more available, and for an in-depth review, you can see Moffat et al., which review a bunch of different extraction tools. So going into some issues that I had during the development. So when I first started exploring feature extraction, it was in the context of Equator. Equator is ROLI's soft synthesizer, and I wanted to get access to the audio data that Equator was producing and analyze it so that I could program some visualization capabilities in Equator. And that would have included, grabbing the audio data from the audio thread. So understandably, a lot of the developers were like, well, don't touch the audio thread, because Equator is going to start glitching out if your analysis takes too long. And this forced me to think carefully about thread optimization, thread safety, and optimized lock-free programming. So the first issue I'll talk about is lock-free programming for real-time analysis. And there is a great talk by my colleague Timur, C++ in the audio industry. It's available on YouTube. He talks about a similar problem. He talks about lock-free programming for audio synthesis, mainly audio synthesis, and he brings up the golden rule of audio programming, which is don't have audio dropout. And when you're doing audio synthesis, this is extremely important because audio dropout can result in junk data being sent to the speakers, so you can damage speakers and damage people's ears. But in the context of visualization, the other way around. So when you're grabbing audio data from the audio thread for the GUI or the visualization, this danger is kind of less pronounced, because if you miss a visual frame, not much bad is going to happen. But for analysis, it's still important because you don't want to be analyzing junk data. Then you'll get junk features. So this is still an important point. One way to approach this problem is by using a lock-free ring buffer, which Timur talks about in good detail in his talk. And the basic approach is that you have a circular buffer, which is being read to by the audio thread. Written to by the audio thread and read from by the analysis thread or GUI thread or whatever you're doing. So if we look at this is like a snippet from my implementation. So on my audio thread, we first set a flag to say that the audio thread is updating the circular buffer. And then we check whether we're wrapping around to the start, just to get our indexes right. And then we write into that circular buffer from the audio that's coming in. So we don't lock anywhere, we just continuously write to this circular buffer. And that happens continuously on the audio thread. And on the analysis thread, we first check whether the audio thread is updating the buffer, and we also check whether the indexes overlap. So this just means if our read pointer is here, we don't want our write pointer to be in the middle of what we're about to read from. So we just make sure that that's not the case. And then similarly, we check for the wrap round, and then we read from that circular buffer into this buffer that we're going to use to analyze. And this is like one of the ways which you can do a sort of real-time STFT implementation and analyze each window as it comes in a thread-safe way. So yeah, I was forced to think about that because I wanted to do feature extraction and spoke to the dev team at ROLI, and they were like, well, you need to think about this carefully because it needs to be thread-safe. So, and one thing that also made me think about this more carefully was that I put my feature extraction tool on GitHub, so it was an open code that everyone could look at. So I wanted it to be up to scratch. Another issue I'll talk about is efficiency versus readability. So if we take three features just as an example, the maths isn't too important here. The thing to notice is that each of these equations involves an iteration over the frequency bins. And basically, we can think about these terms in the equations as like intermediate characteristics. So you iterate over the frequency bins and you calculate intermediate characteristics, which you then combine to get your features. A similar concept exists in the libextract implementation, which makes use of feature extraction primitives, it calls them, which are then cascaded to create extraction hierarchies. So like if you need the mean, you only calculate it once, and then you give it to every other feature calculation that needs it. So I wanted to do a similar thing in my implementation by combining all of these calculations into just one iteration. And the problem with that is that I ended up with, quite horrible function, which is very long and hard to read and hard to make sense of. So, if we want to make this a little bit nicer, we can think about what each part of the function is doing, try to chop it up into constituent parts. So first of all, what we're doing here is we're initializing those intermediate values that I talked about, and then we're using the single iteration to calculate them all. So we iterate through the frequency bins and calculate them all. And then once we have them, we recombine them to just calculate the features that we're trying to get. And so we've broken it up into its constituent parts, and now we want to use that to make it a bit more readable. One thing I probably would have done if I was just a PhD, just an academic, is stick comments in above each part of the function, which would be quite long comments saying, I'm doing this now, and then I'm doing this, and then I'm doing this. But I learned through working with the dev team at ROLI and the JUCE library that it's much better to just make your code readable without comments through function names. So like, just call functions which you can read, and you can see what the code is doing. So we want to break this into individual functions. The problem is that this for loop in the middle, it calculates so many of these intermediate values that it's hard to just extract from this function into its own thing. So the thing to do in this case, the thing I did in this case, is come up with a little helper struct, intermediate spectral characteristics. So on the left you have like the struct declaration, and on the right is a function of that struct, which takes in the frequency data and just calculates all those intermediate values. So now we've kind of encapsulated what's going on in this function into a little struct where you have members and a function which calculates all of those characteristics. So we have our first two steps. We initialize and then we calculate. So yeah, on the left we just declare one of these structs to initialize the features, and then we use that struct's function to calculate those features. And the next thing we need to do is use that struct to calculate the features we're after. So we create a function which takes in one of those structs and recombines the features to the characteristics to calculate our features. Now if we go back to our original function, which is declare the features, calculate them, recombine them to get your audio features, it now looks like this, which is nice and easier to read, because first of all you initialize your intermediate values, then you calculate your intermediate values, and then you calculate your features. And compared to this, it reads off quite like nicer. And in your IDE you can then go in and inspect what is that struct, and you can see what it's doing. So it just makes the code a little bit easier to read. And this kind of development practice came from working with a team who knew the importance of readable code and maintainable code. And I wasn't just working on my own as an academic, and I didn't really care what the code looked like. And the next and final issue that I'll talk about is GUI decoupling. So the feature extractor application is relatively simple. It has multiple GUI components, each of which talk to different aspects of the backend. Some of them talk to the audio, and some of them talk to the analysis routine. And then there's also OSC. I don't know if you can see that very well, but I'll give you a demo of the feature extraction tool in a minute. So there's OSC. There's an OSC GUI components here where you can just tell which IP you want to send to and which address you want to send to. And each of these GUI components talk to different aspects of the backend. And if all of those GUI components were kind of tightly coupled with the backend functionality that they deal with, the code base would quickly become hard to iterate, hard to change. It'd be hard to change the functionality because there'd be a lot of dependency. Again, this is something I learned while working on Equator with the ROLI dev team. And so for that reason, I wanted to try and maintain complete separation between the GUI and the actual back end of the app. One thing that helped greatly with this was the use of std function. We heard a lot about std function in Dave Rowland's talk before lunch. And just to demonstrate how I made use of that, I'll talk about the different tracks. So in fact, I'll give you the demo of the app right now, because I think it makes sense if you know what the app can do before I talk about this issue. Okay, so it's calculating my features in real time. It has, you give it your input, and then it presents you with the available channels from that device, and you can turn them on, turn them off, and set your buffer size. And over here on the right you have OSC, so you can send to this address and this address with this bundle address. And the idea was that I wanted this to be very easy to just open quickly when you're in the kind of live performance environment and setup time is an issue. I wanted to just run this and get it going as quickly as possible. So we have these analysis tracks, and talking about separating the GUI from the backend. We have this kind of GUI representation of an analysis track, and then that's linked to a kind of backend list of analysis routines which are happening independently. So going back to the slides. So on the left we have some code from the GUI track implementation. This is like those audio tracks that I just showed you. So the GUI tracks have a list of feature visualizers that you can see down the bottom, and on a timer callback they update the value of those feature visualizers, and it has an std function called getLatestFeatureValue, which in the timer for loop just goes through all the visualizers and gets the latest feature, the latest value for that feature. That's all implemented without any knowledge of what's happening in the backend. You just encapsulate it all in this class, and you say at some point I want to call that query feature value function, and then you expose this setter for that function wrapper, which in the analysis track you can take in a GUI track and link it to this analysis track by using a lambda here to just set what's happening in that getLatestFeature callback. And this allows you to maintain, like as I said, almost complete separation from the GUI and the backend. So you can develop the GUI independently of what is going to happen in the backend. You can just say, at this point I want this visualizer to update, and so on. And at the same time, you can develop the backend independently and just link the GUI, when you're ready. And so towards like the end of my Eng.D, I began working with this audiovisual arts group, and we did a lot of live audiovisual performances and events, and the feature extractor tool was just still kind of coming together at this point, and the different context of those events meant that there was a lot of feature changes and feature requests that I had to implement quite quickly, and this separation of the GUI made that quite easy to do. And again, it was just learned from working on a commercially released product with the dev team. It kind of made me think about these coding practices quite a lot. So that's the last concrete example that I want to talk about. I'll now move into a wider discussion on the differences in coding practices between academia and industry. So when I was originally thinking about this talk, I thought I could, think about the differences in coding practices and maybe give some insight and maybe talk about how they could benefit each other, different coding practices between academia and industry. However, thinking about my personal experience and reading up on the subject, I realized it's not really, the question is actually, how can academia benefit from coding practices in industry? And what I'm trying to say here is summed up by a nice question on Academia Stack Exchange. And I'm not standing here as a developer trying to look down on scientists. Like, you've just seen some of the terrible code I wrote, and hopefully you've seen how my experience in industry helped me improve that code. And when you think about it, the answer is quite straightforward. In fact, the top answer on Stack Exchange kind of sums it up. So the point is that researchers, they don't develop software as the end. It's like it's a means to getting a publication. So they're continuously chasing publications, and any development they do often is just to assist that research. So the state of the code base becomes an afterthought. It doesn't really matter what the code looks like as long as the application does what it needs to do to facilitate the research. And the other point is that researchers aren't programmers, and often they're not trained in programming. So, for example, like a physicist might teach themselves programming to facilitate a certain avenue of research that they want to go down. That second point might be little bit less important in the area of like audio music information retrieval and audio informatics, because it kind of goes hand in hand with programming. So often you'll find that researchers in this area do have some programming chops, but they still nonetheless don't have the same coding standards that are strictly enforced, and for good reasons, in industry. And the fact that coding practices can be poor or underdeveloped in academia is unfortunate, because it could benefit greatly from improved coding standards. So more robust coding standards could lead to research tools that last longer than the publication that they're built to serve. And these tools could be made publicly available, which would facilitate the replication of studies and the extension of existing studies. And one way that this could be motivated is to reward well-developed research tools with publications. And in the field of MIR, this actually does happen quite a lot. You will see publications that just talk about a new tool for feature extraction, for example. But there are other areas, other fields where this kind of practice could benefit academia. So the ways in which research in general could benefit from coding practices in industry is an ongoing discussion. There are three sort of guidelines that I'd like to point out. I think, can I get a show of hands? How many of you would say you're in, so academia versus industry? Hands for academia, if you think you're in academia. Okay, so, and the rest are industry. So these kind of guidelines might be, old news to a lot of people in the room, but I think they could greatly benefit academia. So first one, style adherence. Adhering to like a strict coding style makes code just a lot more readable and maintainable. So as a researcher, if you come back to some application that you built a year ago for some publication because you have a new idea how you might extend it, if it's sticking to a strict style adherence, you can read what you were doing and know exactly what you were talking about. Whereas if you're not strict about this, you often can't understand the code you wrote even like 2 months ago. So tools is the next one. Like I'm often quite surprised by the number of people in academia and researchers I meet who don't use version control and build applications for publications, and just they have no way of managing it. They don't know what it used to look like and if they can go back to a certain state. And version control is very beneficial for that. And the third one, for me, the most important one, is code review. But at the same, if a researcher is developing code that they know other researchers or other programmers are going to lay their eyes on they're going to try and make it legible and understandable and up to scratch. And this is like one of the things that motivated me to put my feature extraction code on GitHub, because I know it would scare me into making it better code. But at the same time, it's also the hardest guideline to follow for many researchers. You know, they might not have the contacts or the will to show their code to other people to review, which is a shame. But one way to motivate and encourage this practice would be to include open source code along with publications. So Afron Smith has a very good talk on this. He talks about how academia can steal certain practices from open source. And there are many ways in which open sourcing research code would benefit research communities. If researchers, as I said, if researchers were developing code that they knew other people would look at, it's going to increase their motivation to write good code. And also, an open discussion on coding practices within research will gradually raise the bar. And yeah, as mentioned earlier, open sourced research code would allow for replication and extension of existing studies, which is something that's very important in academia. So something that's less clear is whether coding practices in industry can benefit from practices in research. Obviously, we know that industry benefits greatly from output of research and innovation in techniques, but I'm talking about specifically coding practices. And in my opinion, the short answer is no, because industry, like their motivations are different. They want to write. It's in their interest to write manageable, extensible products which are released to mass markets. So, for that reason, they, a great culture of methodologies and coding practices has been developed within industry. That they want to write readable code that new programmers can come in and understand, and they want to write efficient code that won't break. And because these motivations are different than the ones in research, they're much better at writing well-developed code in teams. But one thing that I think industry could benefit from is more like kind of not specific coding practices, but developmental practices. One thing that I felt, and I think a lot of researchers feel when they do their research, is a great sense of ownership, and the feeling that you're working on something novel that no one's ever done before. And that's what kind of motivates you to get the work done and get your publications out there. And I believe, and I have experienced that ROLI, if you can give this feeling of ownership to developers in a company, they will just give more dedication to their work and more enthusiasm about the project they're working on. So if you can maximize the level of ownership and responsibility that developers have, they will approach their work in this kind of more motivated way. This is something that Jules talked about in his opening talk, where the team became like collectively motivated at the opportunity of developing something new. And I wasn't involved in the development of blocks, but because I was away finishing my thesis, but I've definitely felt this feeling of ownership on other products at ROLI, like developing Equator and the Rise, Seaboard Rise. And I think it's something that ROLI does really well and can be of great benefit in industry. So just to conclude, there's a lot that, there's a ton that academia can benefit from if it adopts some of the coding practices in industry. And this is an open discussion. You can go and look at other talks and papers about it. Research could become more replicable and extensible and open if academia took some of the principles of open source, and if researchers publish their code frequently. Researchers can get more from their investment in software development if they follow style guidelines, and if they use their appropriate tools, their development cycle can become a lot easier and less stressful. And if they make the effort to get their code reviewed and put it out there publicly, they will be forced to rethink their coding practices and become a little bit more confident in their coding. And at the same time, developers will give more investment to the development of products if they feel a sense of ownership that a lot of researchers feel often. And that's where I'll conclude.